Hello, everybody. Thank you for joining us and welcome to the Astro 3D ECS Astronomer in Australia seminar series. My name is Dr. Jeffrey Simpson and I'm a postdoc at the University of New South Wales. And my co-chair is Anisha Hashan, also from the University of New South Wales in Sydney. Before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the land, of the unceded lands on which we're meeting today. I'm speaking with you today from the land of the Wallumedegal clan, and my co-chair Anisha and our second speaker, John Lopez, are joining us from the land of the Bidigal people. Our first speaker, Lara Cullinane, is speaking from Ngunnawal country. We pay respects to their elders past and present and extend that respect to all First Peoples joining us here today. So why are we here today? This is a series of seminars facilitated by Astro 3D, the ARC Centre of Excellence for All-Sky Astrophysics 3 Dimensions. COVID-19 has affected our ability to travel and present at international seminars in 2020 and 2021. This is especially difficult for us in Australia because the time zone differences mean that although meetings are virtual, they often are run at 2 or 3 in the morning in our time zone. And so this lack of opportunity to network and present our research from Australia could severely disadvantage junior astronomers who are entering the job market. So we have 2 talks over this hour. Each talk will be 20 minutes in length with 5 minutes for questions at the end of each talk. Please save your questions until the end of each talk. Feel free to use the chat function to ask your questions if you prefer, and Anisha can read them out for the presenter. These talks have been recorded and will be placed on the Astro 3D YouTube channel for educational and scientific purposes. By being here today, you are agreeing to abide by Astro 3D's meeting code of conduct. And I've also already warned the speakers of this, but because of the limitations of Zoom, I will need to interrupt each with about 5 minutes left to let them know they've got 5 minutes left. So onto our second speaker is Dr. John Lopez, who is an astrophysicist specializing in research on molecular clouds and star formation throughout the Milky Way Galaxy. So John, the screen is yours.
Perfect. Thanks for that, Jeffrey. I'm just about to share my screen now. Okay. All right. Thanks for the introduction. Good morning, everyone. I'd like to take this opportunity to thank the organizers of this conference series for selecting my talk. Now, my presentation today will be discussing the work of my recently approved PhD thesis, which would not have been possible without the assistance of my supervisors, Maria Cunningham and Lisa Harvey-Smith. So I'm not going to assume you're all experts in the areas of molecular clouds or star formation. So I'm going to be starting from scratch and giving you the essential information that you need to know to bring you up to speed with my area of research and the work that I've done. Now for a brief overview. So I'll be giving you some background. There are 3 parts to my presentation today. I'll be discussing my research on the Galactic Centre, Planck cold cores, and then the work I did merging both data sets to utilize the RADEX radiative transfer code, but before providing you with a summary. Having said that, let's take a step back and look at the big picture. The image presented before you is that of an artist's impression of our Milky Way galaxy. It has been estimated that our galaxy is home to approximately 100 billion stars, and that our universe itself has just over 100 billion galaxies. Despite their ubiquity in the cosmos, we still do not have a complete understanding of how stars form. One of the biggest issues facing astronomers today is a way of reconciling high mass star formation with low mass star formation. Now, I won't be going into too much detail about high mass star formation, except to say that the gaps in our knowledge of high mass star formation are far more pronounced than low mass star formation. And in contrast, low mass star formation is fairly well understood and follows this diagram here. We start with a dark cloud and dense cores. Over time, gravitational collapse occurs. More time elapses, we have a protostar, eventually a T Tauri star, and then finally a young stellar system. So there is still a lot of uncertainty associated with the first stage of star formation. In other words, the pre-stellar phase, which is before gravitational collapse occurs. And so the bulk of my data today comes from this very early stage of star formation. So how do we actually go about analyzing this early stage? To do that, I analyze the birthplace of all stars, molecular clouds. Molecular clouds are cold and dense environments with temperatures ranging from only a few degrees Kelvin all the way up to 100 degrees Kelvin. On this slide here, on the left-hand side, we have the famous Orion Nebula as observed with the Hubble Space Telescope. And on the right-hand side, we have the same image, but observed in radio with the Nobayama Radio Observatory. As you can see, there are stark differences between both images, and the radio image unveils a population of clouds hidden within the Orion Nebula. So what we do here, or rather what we do with radio telescopes, is that we observe molecular clouds using molecular lines. Different molecular lines allow us to trace different properties of a molecular cloud. Some molecular lines are good at tracing dense features of a molecular cloud, and other molecular lines are good at tracing shocked gas or high density gas. Now, you might be thinking to yourself, John, hang on a minute, why aren't we utilizing hydrogen or helium? Aren't they the most abundant molecules? You are correct. However, in radio, hydrogen gas, due to its symmetric nature, doesn't actually emit until we have a temperature of 500 degrees Kelvin, and this is far too warm for these cold environments. And helium doesn't have any detectable transitions within radio. So we have to use the next best thing, which are proxies. And so an example of a proxy is carbon monoxide, which happens to exist within a relatively transparent part of our atmospheric window. And all that means is we can observe it pretty clearly down here on Earth. And so here we have CO, which is carbon monoxide, and that's good at tracing the widespread features of a molecular cloud. And N2H plus is good at tracing denser features of a cloud, as we can see here on the right-hand side. And so by analyzing different molecular lines, we are able to build up a picture of the molecular clouds that we are studying. And we can calculate properties of the cloud using these molecular lines. These properties include the intrinsic velocity of the cloud, the temperature of the cloud, mass, abundances, and other essential properties. And so by calculating these properties with different molecular lines, we are effectively determining the initial conditions for star formation to occur. And so one other point I want to mention is that molecular clouds are by default hierarchical in nature. In other words, they have dense components, but they also have cores within them. And so using some algorithms, we can determine, or rather differentiate between the different segments or parts of a molecular cloud. So that brings me to the end of my overview. Now on to part one. So for the first part of my research, I analyzed data from the Galactic Centre. In particular, I looked at radio data from a region known as the Central Molecular Zone, which refers to the inner 500 parsecs of our Milky Way Galaxy. And so this is a chemically rich and dense region that's hostile and rather different to any other part of our galaxy. And I chose to focus on this box region within the Central Molecular Zone, which corresponds to a region known as Sagittarius A. So if we just zoom in on this region, one of the reasons I focus on this region is because our galactic center is home to a supermassive black hole known as Sagittarius A star. And close to this supermassive black hole are two large molecular clouds, one of which is called the 20 kilometers per second cloud, as highlighted in the diagram below. And this is just denoted by box label number 1. And the other molecular cloud is called a 50 kilometers per second cloud, and this is highlighted by box number 2. And so the image above and below are also N2H plus. And all this data was observed with the MOPRA 22-meter radio telescope. And so pixel by pixel, the MOPRA telescope mapped out the entire CMZ back in the early 2010s over a period of 3 years, and it mapped the central molecular zone in 18 different molecules covering the 3 millimeter and 7 millimeter wave bands. And this is the work done by Jones et al. 2012 and Jones et al. 2013. And so I analyzed just these two clouds, the 20 kilometers per second cloud and the 50K cloud, to understand their chemistry and kinematics and to see whether the supermassive black hole had any sort of effect on either of these clouds. And now I'm just going to summarize one of the key results from the paper that I published back in 2016. So radio data is given to me in the form of radio data cubes. So where we have X and Y in position, and Z in velocity space. And so one way to analyze molecular clouds is to extract their spectral lines. And so I calculated average spectral lines to each of these clouds, and I applied a Gaussian fitting model to determine properties such as their abundances and intrinsic velocities, full width or half maximum. And so what I can do is, with the results I have from the molecules, I can calculate line ratio plots where I divide the abundances of the molecules by another molecule to determine their relative abundances. And so this is what I did on this next slide. On the x-axis, I have a sample of molecular lines observed in a 3 millimeter waveband. And on the y-axis, I have a molecule, this is in log base 10 scale, and I divided it by 13 CS, which is an optically thin isotope log of carbon monosulfide. And so 13 CS is good because it's optically thin. And so by dividing each molecule by 13 CS, I effectively have a good measurement of the abundance of each molecule in each cloud. And so what I have here, if you just have a look at the graph, is that whilst there are similarities between both the 20 kilometers per second cloud and the 50 kilometers per second cloud, the 20 kilometers per second cloud is enhanced in molecules such as HNCO, which is good at tracing shocked gas, and another molecule, CH3CCH, which is good at tracing dense gas. And so the reason this is important is because other work that I did in my paper showed that basically the 20 kilometers per second cloud is passing by the position of the supermassive black hole. And over time, we speculated that the gravitational potential arising from the black hole and other objects in that area is causing a tidal shearing effect on the 20 kilometers per second cloud, which is one key result. And another key result is that the chemistry is actually similar between both clouds, despite the hostile environments that they are located in. So that brings me to the end of part one and on to part two. So in the second part of my research, I deviated away from the Galactic Centre and decided to look at a data set known as the Planck cold cores. And so let me start with Planck first. So the primary objective of the Planck telescope was to observe the cosmic microwave background. And in order to do that, it had to subtract all the foreground emission across the sky. So in other words, all the gas and dust. However, my team and I were interested in all of that foreground emission because one of the benefits of Planck was that it's an all-sky survey and it effectively unveiled a population of clouds previously hidden within our Milky Way Galaxy. However, the Planck data is rather low resolution. It was about, I believe it was 5.7 arc minutes. And we decided to follow up a subset of the Planck data set known as the Planck cold cores. And so this subset has two key properties. One, they have temperatures of less than 14 degrees Kelvin. And two, they have a signal to noise of greater than 15. And so my team and I followed up this subsample of Planck cold cores using the Purple Mountain Observatory, and we mapped it in carbon monoxide for further analysis. And so what I did was I applied a dendrogram algorithm to this Planck dataset to create catalogues of results, and dendrograms are good at quantifying the physical properties of the clouds. So what are dendrograms? Okay, so simply put, a dendrogram is a tree diagram. Of course, it's a little bit more complicated than that. If we were to classify the properties of this tree, or really any tree, it effectively boils down to three features: the trunk, branches, and leaves. Dendrograms follow this same principle. Consider this diagram here, this 2D schematic of a cloud. We're starting from the outer edges, we have the trunk. This would represent the diffuse emission within a cloud. Leaf 3 and the branch represent denser components of a cloud, and leaves 1 and 2 represent the densest components of a cloud. For example, the cores within a molecular cloud. The dendrogram for this schematic would look as follows. We start at the bottom with the trunk. This segments out into leaf 3 and the branch, and then the branch segments out into leaves. Trunks are always at the bottom of a dendrogram and leaves are the highest components. So let me now show you a few examples of what the dendrogram looks like for our results. On the left-hand side, we have 12CO and 13CO moment zero images. So what moment zero images are is, if you refer back to my example of data cubes, what I've done in the z-axis is I've integrated across all the velocity channels and basically flattened the data cube to create one integrated emission image. That's what these moment zero images are. So with 12CO, there isn't too much going on. So unsurprisingly, the corresponding dendrogram is just a simple trunk. However, in 13CO, we see a few pockets of emission here in a diagram, and correspondingly, our dendrogram is a bit more complicated than that. So I have utilized the dendrogram algorithm of Rosolansky et al. 2008, and I applied it to the Planck-Cold cores dataset, effectively producing the first decomposed dendrogram catalog of these Planck-Cold cores. And so this catalog is effectively a catalog of properties such as the average temperature, full width half maximum, intrinsic velocity. And using a rotation curve, I was also able to calculate other properties such as mass and luminosities of all these Planck-Cold cores. And the Planck-Cold cores are important because they are believed to be at the very earliest stage of star formation, even before dense cores have even really started to form. And so what I can do with my catalogs is I can test whether these objects actually form known star forming relationships. And one of these relationships is known as Larson's laws. So Larson's laws are scaling relationships between the physical properties of molecular clouds. And so there's a lot going on in this diagram, so I'm going to break it down for you. So we start here with 12CO, Larson's first law. This is a relationship between the radius of the cloud and velocity dispersion, both in log base 10 scale. And so what I've done here is, of course, I've plotted my results, and I've plotted the work done by other authors such as Rice et al. 2016. He used 12CO data from the entire Milky Way Galaxy, and he also utilized the dendrogram algorithm. Solomon et al. 1987 used low resolution 12CO data from the Milky Way, but he didn't use the dendrogram algorithm. And Bellardo et al. 2008 did not use the dendrogram algorithm, but he utilized a data set from resolved extragalactic molecular clouds. And so what I want you to take from this diagram here is that even though we have some overlap between our results in a Milky Way galaxy compared to clouds elsewhere in the galaxy and in resolved extragalactic clouds, there is no clear relationship between velocity dispersion and radius. At best, for Larson's first law, the correlation is weak, or rather tenuous. This is also a similar case for 13CO. And so I don't really have any point of comparison here, but what you should know is that the 12CO fit versus 13CO fits is comparable. For Larson's second law, which is virial mass versus luminosity, the fit is much better. And however, we observe still a similar trend, and our gradient is much shallower. Similar case for 13CO. And for Larson's third law, which is luminosity versus radius, this is arguably our best fits. But we still observe a similar trend here. And so this is important for a number of reasons. When Richard Larson came up with his laws in 1981, he took a star-forming data sets of objects across a different set of time sequences from the star formation process. And so all of my Planck-Cold cores are from the very earliest stages. So my results are important because it shows that Larson's laws hold for my data set, even at this very early stage. And this also indicates that Larson's laws are most likely to be universal.
That's 5 minutes.
Okay, perfect. Thanks for that, Jeffrey. This indicates that our data set is most likely unique and needs to be investigated further. And we suspect it's most likely unique because it exists at this very early stage of the star forming process. On top of that, we believe that turbulence has a major effect on the molecular clouds. And so I just realized I hadn't shown 13CO fit, which, yeah, between 12CO and 13CO is identical here. And so the effect of turbulence is substantial. It's effectively preventing gravitational collapse from occurring, as is eloquently demonstrated on this slide here. So that brings me to the end of part 2 and moving on to part 3. So RADEX. So RADEX is a non-LTE, so where LTE stands for local thermodynamic equilibrium, ready to transfer code. in all of my previous work, I assumed LTE conditions for my molecular cloud. So in other words, I assumed generalized conditions about the state of the cloud, including the fact that the excitation temperature is equal to the kinetic temperature when I did my calculations of column density, which is just the amount of gas along the line of sight. And so what I did with RADEX was I thought to myself, okay, why don't I apply RADEX to both the Galactic Centre datasets and the Planck cold dataset to test whether if we apply more stringent conditions to the physical properties of the cloud, how would this change our results? In other words, how would non-LTE properties of the clouds compare to the LTE properties of the clouds? And so what I did with the Galactic Centre results was, because I only focused on two clouds, a 20 kilometers per second cloud and a 50 kilometers per second cloud, and I had 18 molecules for both data sets, I was able to constrain three parameters quite tightly when utilizing the RADEX code. And all I had to do was check whether our kinetic temperature assumption was equal to our excitation temperature assumption in the LTE calculations. And to do that, I varied the kinetic temperature assumption from 20 degrees Kelvin all the way up to 120 degrees Kelvin to see what effect that would have on the output of the RADEX code. And the output of the RADEX code is the optical depth, the excitation temperature, and the radiation temperature of the molecular cloud. And so when I investigated that parameter space, what I found was that in general, the LTE assumption that I made and compared to the non-LTE assumption was in fact fairly similar. And this also applied to the optical depth and the radiation temperature of the cloud. And so this is important because it tells us that the chemistry between both clouds is identical despite the hostile environment. And on top of that, we found that in general, the molecular clouds in the galactic center are subthermal. So in other words, sometimes the excitation temperature, even though it can be identical to the kinetic temperature, is lower than the kinetic temperature. So I also applied it to the Planck cold cores. Of course, here in this case, because of the special properties of Planck cold cores, I could only investigate the temperature between 5 degrees Kelvin and 15 degrees Kelvin. And so on this plot here, which is just, this is my second last slide. So I plotted excitation temperature versus H2 density. And so these blue circles refer to the temperatures that I used. And so when I investigated it at 5 degrees Kelvin, above a certain density threshold, I found that the excitation temperature is equal to the kinetic temperature. But this is most convincing at 5 degrees Kelvin for about 80% of the results, but it's less convincing for the kinetic temperature at 10 degrees Kelvin and 15 degrees Kelvin. And so this is important because what this shows us is that all the Planck cold cores have similar temperatures at low temperature regimes, but it's less convincing when we get to high temperatures. So as my time's about to run out, I'm going to leave you with my summary slide. Thank you very much for listening. Happy to answer any questions.
Thank you, John. I will pass over to Anisha to share the question session.
If there are any questions, please raise your hands or unmute yourself and ask it. Wait a second.
Sorry, no, that was applause.
Yes, please. Hi, Eric. Could you please unmute yourself?
Yeah, thank you, John, for the very nice talk. I have a couple of questions. First, did you differentiate galactic center cloud and galactic disk clouds? It seems to me that in literature, they follow quite different Lawson relations.
Yes. So, sorry, can you just clarify that? So, when you're saying I differentiated them, what do you mean exactly?
For example, they have different slopes or different. They just basically follow different trend lines on the plots. Are you aware of that, or is it?
Yes. Do you mean in my plots for Larson's laws, or?
Yeah, essentially, yeah.
Oh, okay, yeah. So that is a good point. I don't believe I investigated that too much, but I didn't include, so all of my data points here for Larson's laws. So these don't include any of the clouds in the galactic center. These are all just from known star-forming regions. So I didn't include any galactic center clouds here.
Okay, I see. So it's basically galactic disk as well.
Yeah, that's right. Just galactic disk, pretty much.
Yeah. Maybe a quick follow-up question. Have you tested the constant surface mass density of the Larson's law?
Good question. So I did, but I don't have the plot here. I think you're referring to, when you say constant mass surface density, do you mean just like the relationship when we just rearrange Larson's laws? I think it's like surface mass density versus, is it radius, or was it one of those properties? I think I've done that, but I'm not entirely sure if I plotted that.
Yeah, I think basically Larson just discovered the clouds in the Milky Way has a constant surface mass density, whatever it is, versus whatever it is plotted against. So do they appear to be a constant to you, or do they vary? Do they have vary surface mass density?
Okay, good question. So I don't have the plot here, but I do remember making that plot, and from recollection, they had fairly constant surface mass density.